Hello dear students, welcome to third part of the topic thermodynamics, and we shall be talking about work today. We shall be building on the concepts that you already have learnt in physics, that is mechanical work, which you learn only as work in your earlier classes. Work, the product of force and displacement taking place in the direction of the applied force. So let us suppose I have an object here and I move it, I apply pressure on it, I apply force on it, and this object moves in that direction. That means work is being done by me. Electrical work, that means the energy which is flowing, the work which is happening because of the flow of charge or current through a conductor. Again, going in a roundabout manner, potential difference is the amount of work done per unit charge. That is how you define it. So work, in other words, is the product of potential difference and charge. Charge can be replaced by the product of current and time. We shall be using this concept under the topic of electrochemistry, but for now we'll let it take a break. Third concept, third extension of the work, pressure volume work. This is the work that we are going to discuss in greater detail now. When you're talking about pressure volume work, what does immediately come to mind? Yes, a gas. So what we've got over here is we've got a gas in a cylinder which is trapped by means of a piston, and there's a certain pressure that we are applying from above. Before we go on to talk about pressure volume work, which is nothing but the work of expansion and contraction, we have to define some terms. A reversible process. Now you have read about reversible reaction. That means a reaction in which the products can reform or go back to the reactant state, right? This is an example of a reversible reaction. A reversible process is something similar. A process which is taking place so slowly that at any point of the time the system is always in equilibrium with its surroundings. So I have this pump being moved so slowly. If you notice, I've already moved it. It is being moved so slowly that at any point of time there is always equilibrium between the air inside it and the surroundings. So what do we have over here is this is always in equilibrium. See, we are going to move it infinitesimally slowly, very slowly, so that the dynamic equilibrium is always maintained. So this is what we mean by a reversible process. An irreversible process would be something wherein there is a sudden expansion or contraction so that this equilibrium is disturbed. That means, so let's suppose I have this pump. So this would be kind of an irreversible process when defined thermodynamically. That means a process which is taking place fast. Anyway, we are not concerned with irreversible processes for now because that requires many other assumptions as well. We are going to concentrate on a reversible process, a process taking place infinitesimally slowly so that there is always an equilibrium between the system and the surroundings. In order to trap the gas, in order to keep the gas at volume V1, there's a certain pressure that we have to keep applying on the piston, and that pressure is PEXT. Area of the piston is A. Volume V is the generalized alphabet that we are going to use, but we shall change depending upon whether it is initial or final volume. The area of the piston is A. Now when I move this piston out, just like you saw me moving the pump a little up, I will move it infinitesimally slowly. That means very slowly, so that the system and the surroundings still remain in equilibrium. Now when we move this up, the movement of the piston is denoted by a very small change in the height of the piston, denoted by dl. In other words, the volume of the gas will also change by a very small amount. That's an infinitesimally small amount. Volume is area of cross section into the height, right? So we have A into dl. So because this is involving a very small change, infinitesimally small change, the change in volume will also be given by a very small value, that is dV. The external pressure has been reduced by a very small amount, dP. So the new pressure is P external minus dP. Now, in order to keep the system in equilibrium, the gas tries to expand. It has expanded. In other words, there's some work being done by the gas. That work is what we want to talk about, and that is what is called as the pressure volume work. On the other hand, if we press the piston down, in that case, there is work being done on the gas when you are applying pressure on the gas in order to reduce its volume. So that's also pressure volume work. So thermodynamically we are going to talk about the pressure volume work, but as I said earlier, we shall be building on the base that you already have, and that base is the relation between pressure and force and work and force. Pressure is defined as the force acting per unit area, and work we've already defined product of force and displacement. So taking on from here, we can also say work is pressure into the area into the displacement. The pressure that we are applying now is P minus dP. The area of the piston is A, that is the assumption we have taken over here, and the displacement of the piston in the first step, where we have moved it infinitesimally small distance, is given by dl. Now as we have carried out here, area into the small displacement is given by the small change in volume dV. D doesn't stand for displacement. D here means the differential, basically indicating that there is a very small, infinitesimally small change in the volume. So we have P minus dP into dV. We open the brackets, pressure into dV, dP into dV. Now if you have two infinitesimally small values being multiplied by each other, so let's suppose I have 0.001 multiplied by 0.0001. So this will give me again a very small value, that is of 10 to the power minus 7, which will be very small compared to the value we will get here, P into dV. So that is ignored for this derivation at this stage. At advanced levels, you may have to take other different variations, but for this stage, you know that P into dP into dV is to be neglected. So we have the small amount of work being done by the gas, because again it is dW. So the infinitesimally small amount of work being done is the P external into dV. If now we carry out this, keep on carrying out this process by the same infinitesimally small changes, such that the volume of the gas changes from V1 to V2. In other words, the gas expands from a volume V1 to a volume of V2. That is representing the change in volume. Delta V is what we shall use. So the total work done in this process would be P external into delta V. Delta V would be the change in volume. Here if you notice, minus sign. Why a minus sign? Work is being done by the gas in expansion. That is why it is by convention taken as negative. Please remember in thermodynamics, by the system minus, on the system plus. Anything removed from the system becomes minus, anything added to the system becomes plus. What will happen if this external pressure is zero? Can we have a situation where the external pressure becomes zero? Is it possible? Yes. If this gas is allowed to expand in an area where there is no pressure, that means there is vacuum. That is what we mean by external pressure becoming zero. So in that case, W would be 0 into delta V. What will be the value of the work done by the gas under such circumstance? Yes, it will be taken as 0. The work being done now by the gas is 0. Let us now go on a step further. Let's introduce the concept of temperature as well. And we are talking about an isothermal process. Now, if you go back to the definitions we had done, iso means same, therm is temperature. That means in this process, temperature is remaining constant. Going back to dW is minus P external into dV. Your external pressure is slightly lower than the internal pressure after you have moved the piston up. So, dW can be written as the internal pressure of the gas minus dP. What is the point of talking about internal pressure over here? Simply because it is easier to measure the pressure of a gas rather than the external pressure, the pressure of the surroundings. Because pressure of the surroundings, there are various factors. So here we will switch on to the pressure of the gas, and further on we will just call it as P gas rather than P internal and P external. Again, opening the brackets, multiplying, we have minus P internal dV plus dP dVs. Now, the small amount of work done in this case is pressure of the gas into dV, which is the same expression that we had derived earlier. We need to introduce the factor temperature. So PV is equals to nRT is our ideal gas equation, assuming that the gas particles don't interact with each other. So we have pressure can be expressed as nRT divided by V. So the infinitesimally small amount of work done is minus nRT upon V into dV, that is the differential V. When we have to find out the net amount of work when the gas volume changes from V1 to V2, that means we are now talking about summation. We are not talking about division, we are adding up all the small amounts of work. We use the system of integration. Here you will have to use a bit of your mathematical concept. If you are not a mathematics student, you need not worry. What formula we are applying over here is 1 upon x into dx. That means integrating the reciprocal of x with respect to ds, we get just natural log of x. Natural log of x means to the base e. So W, the total work done is minus nRT natural log of, now here we are integrating between the limits V1 and V2. In other words, the volume of the gas is changing from V1 to V2. So we get over here natural log of V in the limits V1, V2, natural log of V2 by V1. It's easier for you to convert it to base 10 because that is the system and those are the logarithmic tables that you are used to. If you are using a calculator, you can work with the natural log system as well. But if you are referring to the tables, you would rather prefer to change it to base 10. So we have W is minus 2.303 nRT log of V2 by V1. That is the work of expansion of the gas under isothermal reversible conditions. We can also express this equation in terms of pressure. P1 V1 is equals to P2 V2. So from here we can get V2 by V1 would be P1 by P2. So V2 by V1 can be replaced by P1 by P2. Now work is a thermodynamic quantity. So what are the characteristics of this work? As I said, on the system, work done on the system plus by the system minus. Work is a path function. How is it a path function? See here, work done, P external into delta V. If I'm carrying out the same process but under vacuum, that means external. Again, the gas is doing work by, the gas is expanding, but it is expanding, against vacuum. That means I'm carrying out the process under external pressure being zero. In other words, what will happen is the work becomes zero. On the other hand, if you are carrying out the process under constant temperature conditions, this is the expression that we use. Work is an extensive property, a property which is depending upon the number or the amount of the gas that you have taken. So, if you notice this expression, W is minus 2.303 nRT log of V2 by V1. If you recall over here, N is the number of moles of the gas. So, it is depending on the number of moles. The last point we have here, in an adiabatic process, during an adiabatic process, work done is equals to the change in internal energy. We shall talk about this later on as we develop and as we deal more with adiabatic processes. For you to be able to relate to this derivation, it would be in your best interest to derive it yourself, to practice it 2-3 times. Unless you write and do it, it does not stay in the mind. Scientists have shown that there is always a correlation between what you write and what you can recall. So try and write this derivation yourself in order to have a better understanding of it. And of course, attempt at least 4 to 5 numericals based on this concept in order to get a better hang of it. Hope you have a good day. Do let me know your feedback. Highly appreciate it. Thank you for watching.